Hey guys, what's going on? So today we're going to be talking about charged quantum fields. We're going to be introducing the nomenclature of charge into our fields, and we're going to be able to start to understand these fields as sort of mathematical intuitions of particles or mathematical concepts that construct particles, okay? So with that being said, make sure to hit the like and subscribe button. Make sure to go onto my Patreon page if you want to support there, or you can become a member here on YouTube. So let's go ahead and get started. So we're talking about charged quantum fields today. Let's go, we're going to go deep into this. We're going to look at the mathematics behind this, and then we're going to move on from there, talk about the number operator later. And so here we're discussing charged fields. Charge is an internal symmetry of our fields. So we looked at this picture before. Throughout this entire series, we have taken this route of, or so far, we've taken this route of doing space-time transformations. The space-time transformations look like this, where instead of moving the field itself, what we're actually doing is we are moving the underlying point within that field. So I have this X highlighted, right? So this is the space-time, space and time, right? And so time should be also highlighted here. But the idea here is that we have this thing here, the underlying coordinate system, not the field. The underlying coordinate system is what's being shifted, okay? And when we shift that, if there's going to be something about this field that doesn't change, okay? And so we've done that. What that was energy and momentum, right? So when we did this change, we found out that the thing about this field that didn't change was energy and momentum. Now let's take this route. We're going to take we have our field, and we have our underlying coordinate system. The underlying coordinate system is going to stay the same now, but instead of rotating the underlying coordinate system, we're now going to rotate just the field. Okay, so we have this part here. We're rotating it now 90 degrees. I keep track of a point with the red dot, and now what we're doing is I've highlighted the actual field. We've rotated the field. So that's an internal transformation. This internal transformation again. There's going to be something about this field that remains constant during this transformation, and that thing that remains constant, we're going to find out what that is in this video. So we've talked about this already. That was energy and momentum, okay? And we calculated the energy and momentum for these fields for the real scalar field and for the complex valued scalar field. So we're going to take a look at the complex value scalar field now and do this type of transformation. Okay, so we're going to find internal symmetries of our complex valued field, and one way to and we'll see that this results in different charges, okay? Specifically, we want to calculate internal global symmetries, okay? One such global symmetry can be seen to look like this. All right, so we start off with our original field, and then we rotate it or shift it by e to the I theta. Theta is the degree to which we're shifting that field or rotating that field, okay? And if we do that to this, well, we have to do that to our conjugate field as well, and we have to apply the complex conjugate as well. So when we do this transformation on our Lagrangian, what ends up happening is that because this is global, transformation, i.e., when we say global, we mean that theta is not a function of x and t. So if we had, for example, this theta here was a function of x and t, well, this would be local, right? But since it's not, since it's just a constant, it's global. Local, so this is a global transformation, and this global transformation then is being applied in this way, and we apply it to the Lagrangian. Well, we just get the Lagrangian back, right? Because the e to the i's are going to cancel because we have This is essentially the denominator because it's a negative exponent. This here is in the numerator, so they're going to cancel out. And what we get is just the same thing back again, right? This guy is right here. This doesn't change. This guy doesn't change. And these guys don't change either. So recall the difference now between our internal and space-time transformations. So we have these guys. We dealt with this already, so now we're going to focus on this internal transformation. So let's go ahead and start. For a complex valued scalar field, we have two internal symmetries, right? So initially we just looked at, for a real value scalar field, we had Lagrangian, right? We had our Lagrangian density and with respect to d mu, and then we did this guy here like this, and then we had our, this pen is always doing weird stuff, and then we had well we had this bit here, right? This bit right here, and we had no that's this right here. We also need this guy here. So the point I'm trying to get at is that we actually have a little bit slightly more complex thing we're dealing with, which is this extra derivative of the complex conjugate as well. And when we do that, we get these guys here, right? Because the derivative of the Lagrangian with respect to the derivative of the complex conjugate, well, if we look back at our Lagrangian, we have this guy right here, right? This guy. So what the derivative of this with respect to this, well, this is what's going to come out. So we have this that's going to give us our complex conjugate as the derivative, which is how we get these guys here, right? So we have not complex conjugate, complex conjugate, complex conjugate, not complex conjugate. And then for these guys are going to stay the same, right? It's just like multiplying both sides by that small change for each. So this is where the crosstalk happens, right? Because the crosstalk happens when we have here shows up here, and this shows up here. So there's some crosstalk happening there. So there are a couple of differential equations, and what we're going to do now is we're going to take these guys. We're going to now define our internal symmetry, right? We're not really redefining anything. This is just more general, right? This is for the case of real, right? Because these are just real valued. But for the case of complex, we need both of these guys, okay? Because we need to be able to include that complex conjugate. And we're going to set that equal to 0 because the derivative of this thing is going to be 0, right? So we actually need derivatives out in front of this. So we need derivative of that, okay? And so what we get then is this, right? So the derivative of this, well, we just split this up. This is the temporal part. And then this here is the spatial part. Multiplying both sides by I then will give the form of the continuity equation that looks like this, right? Because when we then divide both sides by I, we're going to get a positive, we get the positive sign and the negative sign. So this here is the probability. So this here is the continuity equation, right? The continuity equation, if you don't recall from classical mechanics, I'm saying recall as if we actually went over this. We actually didn't go over this. But the continuity equation is the change in the density plus or minus, or actually I like to think of it like this. The change in the density is equal to negative the change in the current, right? So, and the way I like to think about this, to remember this, is if I have some density, actually I'll go like this. If I have some density, well, and we have some stuff in this density, say particles, we're saying that the time change, if this thing's moving outside of the density, that means the density itself inside is going to change over time. So if some of these guys are moving out, right, they're moving out, and so the density is changing over time, well, that is related to the current moving out of the box, right? So that's the current moving out of the box. So this is J, and then inside is the density. And so what we're seeing now is that this density, what we have essentially is that this thing, this J, represents something akin to a probability density for the continuity equation, or is akin to something that obeys the continuity equation, in other words. We can think of this pictorially as, again, what I've just drawn up here, but a little bit more sophisticated, is we have this volume. Inside the volume, we can calculate the probability density by this equation, right? That's this equation right here. And then we can also calculate the probability current as well. The probability of current is the probability of there being current outside of this density. And this is a three-dimensional scalar field. Okay. All right. So our conserved internal symmetry behaves according to the continuity equation. We're going to multiply this object by a constant, so our conserved quantity becomes this, right? So in some sense, we don't say that this is equal. We're not really saying that this is equal. It's proportional. And to make it equal, we add this proportionality constant. And so the proportionality constant is what's going to be the big thing here. This is the charge. Okay, so we have charge inside of some volume, okay, and then charge escaping the volume. And so we can calculate the time change of charge inside the volume by calculating the spatial change flowing out of the volume of that charge. So integrating over a defined volume, then, this is our defined volume element, we get, we're integrating this guy over a defined volume element. We have our QI in front, we have this, which is right here. So now all we have to do is calculate this mathematical object in terms of our operators. So let's go ahead and do that. So here's what it is, right? So this is this thing is right here, right? Because this thing, let's see, is right here, and then this thing, the change in our field, is our canonical momentum for our field. So we have all these things, right? We have these things. We've calculated these already. And so those are all these guys, right? These are all these guys. And so we plug these in. And here, this is a lot of math. So let's go through this. It actually won't be that bad. We're at a point now where we've done this a lot. We've sort of done this type of calculation a lot, to the point where we don't really need to, we're just going to briefly go over it. If you could pause this if you want. And I think as I'm looking at this, I need an omega prime right there. So sometimes I miss typing stuff in. So we have all this, right? So we're just literally plugging these guys into this, and what we get is all this. We multiply everything out now, so we have BA, so B and A, over K prime K, right? So K prime plus K. And so we multiply all these out, we get all this. And then from this, we use our Fourier coefficient, or our Fourier identities that we've been dealing with for a while now, and we put all those in, and ultimately what we get we get to this point here, because a lot of these guys are going to then collapse the k primes to k's. Okay, and then we use the commutation relationships between B dagger, and A dagger, and ultimately what you get is this guy right here. Okay, this all of this is just sort of mindless math. It's not that's the stuff that we don't. We sort of established this math already. Okay, we've done this a bit, which is why I'm sort of blowing through this a little bit faster now, because if you want to, again, if you want to go through this, you could just pause the video and you can go through this yourself. But from here, then we get this here, and this here looks an awful lot like our Hamiltonian, with the exception of we have this Q right here, right? So this thing, so if we look at this, we have our current, right? This is our conserved current, and so we can look at this and we can say, well, some things are interesting here, right? This thing here, if we just look at this, we're integrating over some volume, right? So this is our volume, and when we integrate over this volume, we have something minus something else times this. Well, these kind of look like, if we put the number of particles inside this volume, integrate over the volume, that would seem to make sense. We have the number of particles, and then we attach charge to that type of particle. This almost seems to look like, these guys almost seem to look like some sort of number operator. And we're now hinting towards this notion of a number operator. These things look like they might give us some idea of these. These things might give us some idea of how many particles are in our volume. Okay, then you attach a charge to those particles, and you have a total charge inside your volume. So, and that's exactly what we're going to do here. We're going to call this thing NaK. This is the number of particles of type A, right? And the number of particles of type A, those are going to be associated. Those are associated with our phi field, and then our phi bar field. So, in some sense, this thing here, these were the coefficients for what we're going to call a type A particle. Type A particle is a particle of the field that's described like this, and type B particles are going to be particles that are associated with the complex conjugate of that field. Right? So, depending on how you label this, right, this could be phi, and this could be phi, like that. Depending on how you label things, we just need to understand that this here is a prescription for what we're going to call a number particle, or a number operator, and it's going to give us the number of particles associated with that field and the number of particles associated with its complex conjugate. So these things are really just related to each other by the fields, which are complex conjugates of each other. Okay? And then this is the charge. Na is the number operator with eigenvalue Na, which is going to be the number of particles with free momentum k. And then Nb is the number operator with eigenvalue Nb, with number, which is equal to the number of particles with free momentum k, right? So we have our field, right? So we have our field in some volume. Okay, we have our field in some volume. This is our scalar field. We have cold values, say, over here and over here, over here and over here. Okay, so this is our field. And then we have complex conjugates of the field, right? So at every point here, at every point in this volume, say right here, we have phi bar. That is our field operator. And then we also have, at this point, phi. And these two are related by complex conjugation. All right. And associated with this guy is going to be some operators, A and A dagger. Associated with this guy is going to be some operators, B and B dagger. And these things are going to tell us the number of particles that are associated with these fields. Okay. As they've told us also the amount of energy associated with the field also, right? So they create and annihilate or create and destroy. I'll just say destroy energy levels. And they also create and destroy a number of particles. And what we're going to see in the next video is that we've already established when Hn, our Hamiltonian, is applied to A of K, right, applied to some energy, H of K, or A of K in the context of H, well, that's the eigenvalue is just E minus omega n times A of K times E, right? We've said this, right? This was our annihilation. We've taken some energy away. Similarly, we've also said H of N A dagger of K to our energy level. That's going to equal E plus omega N A dagger K times E. All right. And then what we're going to find in the next video is that NA, and these actually held true also for, this holds true, or holds the same, for B and B dagger. What fundamentally differentiates then A from B is the type of particles, and they're the number of particles that they, or the type of particles that they associate with. The B particles are going to take away the complex conjugated particles, or the complex those are particles of opposite charge. Okay, which is why we have that charge. So it's not that the charge is a different number. It's just opposite. It's a complex conjugate of that. Right. So, and what we're going to find again is NA. That's going to be our number operator. At K, number operator for, so this is the number of particles with a certain momentum K. A dagger, we'll do A K for some total number of particles. We'll call that we'll just call that N, big N for right now. It's the total number of particles. Well, this is going to take away particles from this state, right? So the eigenvalue then is going to be, or for in the context of this guy, is going to be NA, or total number of particles. We'll just say T total minus the total number of the total number of particles minus number of particles. See, number of particles. number of particles of type A at momentum K. All right, so that's going to be the eigenvalue for this thing times A. This is really annoying. K, and then total number, that's state. So this is what's going to happen, and we can do this for a dagger. That's going to add. We're going to have an addition sign if we have a dagger. If we have B, well, this is going to change to a B, and if we have B dagger, that's going to be plus as well. All right. So we've talked about this. So we're hinting towards this. This is what we're going to talk about in the next video, right? So we have now the total charge inside some volume given to us by our quantum fields. And so in the next video, we're going to talk about these number operators. We're going to see how they work. We're going to see what, and we're going to sort of cap off our understanding of these scalar fields, and we're going to move on to spinors. So with that being said, make sure to hit that like and subscribe button, and I'll see you guys in the next video.